In today's discussion, we're going to be talking about the Fundamental Theorem of Calculus. And this is a theorem that relates integrals and antiderivatives. Remember that antiderivatives are what we studied a couple of weeks ago, and this is where we have a function and we think about, well, what other function has this function as its derivative? It's kind of like the opposite operation to the derivative. And the integral was this measurement of the area that sits between a function and the x-axis. And the fundamental theorem is going to draw a connection between these two. And there's two parts to the fundamental theorem. The first part talks about continuous functions. So let's say that we have a continuous function f. And then we're going to look at a different function, capital F, which is defined in terms of an integral. Specifically, it's the integral between t0, some base point, and x of lowercase f. And here we've switched to using the letter t in this f because we don't want to be conflicting with the variable x that we have in the bound. So here's our variable of the function, and then our t is just kind of used inside of the integral. Now, what does this function look like as a picture? Well, if we draw ourselves some axes, and we draw f of x, let's say that this is f of x, then we have some base point t0, and then given any value, let's say a, an x value a, then f, capital F of a, is going to be the area between our function f of x and the x-axis. So it's going to be this pink area that I'm shading in right now. So given any x value, this function capital F is going to shade in one of these pink areas between little f and the axis and return the area. And the first part of the fundamental theorem tells us that the derivative of this uppercase f, f prime of x, is equal to lowercase f of x. So what does this mean? This means that uppercase f is the antiderivative of lowercase f. So there's our connection right there. The way that we solve these integrals is we use the antiderivative, and that is going to be made even more clear by part 2 of the theorem. And part 2 tells us exactly how we want to compute these integrals. So let's say that we're trying to integrate f of x, or f of t here, from a to b. So here we want to know the area under f of x, or between f of x and the x-axis, between x values a and b. So going back up to the picture, we're trying to compute this white part of the graph. And well, the way that we do this is that we can write this as a difference of two other integrals. So here we have the pink one, which we know is f of a, and now I'm going to shade in the blue one, which goes from t0 all the way up to b. And we see that the thing that's light blue now is what we care to compute. And by using the pink part and then the entire blue part, which we can both write, here we have the integral from t0 to b of f of t dt, and the integral from t0 to a of f of t dt, we can write an expression for the integral we're trying to solve. Right? The full blue part minus the pink part gives us this light blue part, which is the integral that we care about. And now we use part 1. And we use the definition of this function f, uppercase F. And we see that this is f of b, and the second one is f of a. So the way we compute the integral we start by taking the antiderivative and then we want to plug in our endpoints, and then we want to do the subtraction. This is kind of a cool idea. We can compute the area under this curve simply by plugging in to the antiderivative at the endpoints. So that's pretty cool, and we're going to make use of it a little bit later in the discussion. So now that we've gone through the fundamental theorem, let's take a look at the exercises. So exercise number 1 tells us to consider this continuous function, f of x. Does it have an antiderivative? And if so, what is the formula for its antiderivative? And this right here is exactly using part 1 of the fundamental theorem, which told us, right, that every continuous function, little f of x, has this function uppercase f, which is the antiderivative. So we can write that right up in question number 1 and say that yes, it does have an antiderivative, and its antiderivative is given by this uppercase f, which is the integral from some base point up to x of our lowercase f. Okay, and now for question number 2, this is again going to be using the first part of the fundamental theorem. Here we want to compute the derivative of this uppercase f, and like it said in the first part of the theorem, the derivative of uppercase f is going to be the inside function, this lowercase f. So if we let lowercase f of t be t cubed cosine t to the 7th, then we use the part 1 again of the fundamental theorem to write that f prime of uppercase t is, well, this is going to be f of uppercase t, which is t cubed cosine t to the 7th. So both of these first two questions are applications of the first part of the fundamental theorem. Now question 3 is going to make use of the second part of the fundamental theorem. This is the part where we compute an integral by taking the antiderivative and then computing the value of the antiderivative at the endpoints. So let's take a look at question A. Here we're given an integral from 0 to 3 of some polynomial function. And what we want to do to start is we want to take the antiderivative of the function inside of the integral. Here, this is just using the power rule for integration, or power rule for antiderivatives. And that tells us that the antiderivative of x to a power, we compute that by adding 1 to the power. So here x squared becomes x cubed. And then we divide the coefficient in the front by the new power. So we're going to have 5/3. Okay, and then we do this for all the terms. So we're going to have x squared in the second term, and 6 divided by 2 is 3. And in the last term, well, 3 is 3x to the 0. So adding 1 to x to the 0 gives us x, and 3 divided by 1 is still 3. And now we're going to introduce this notation, this vertical bar over here, and we're going to put our endpoints of the integral, so 0 and 3, over here. And this notation tells us to plug in 3 into this function we just found, plug in 0, and then subtract them. So we'll do that now. So if we plug in 3, we're going to have 5/3, 3 cubed, minus 3, 3 squared, plus 3 times 3. And if we plug in 0, well, we can easily see that all of the terms in that function are going to go to 0. And all that we have left now to finish this integral is to simplify. So here I'm going to do the 3 cubed, and then divided by 3 is just 3 squared, times 5 gives me 45. Then the second term is 3 cubed, which is 27. And the third one is 9. And if we do that addition, then we get 27. So the value of this integral, the area under the curve, 5x squared minus 6x plus 3, between x equals 0 and x equals 3 is 27. Now, how would we do question number B? How would we do question B? Because here this kind of looks weird. We might be thinking maybe this is the quotient rule. But here, the way we want to approach this is that we want to rewrite this into a form that we know how to take the antiderivative of. So namely, the best thing that we could do is to get it to look like a constant times t to a power. And here, using our laws of exponents, we see that this is just 8 times t to the negative 2. And now we're in the case just like part A, where we're ready to take the antiderivative. To take the antiderivative, same as before, we're going to add 1 to the exponent, so t to the negative 1. And we're going to divide our coefficient 8 by negative 1, the new exponent, to get negative 8. And then we're going to add this bar notation to tell us that we're going to evaluate this from t is 1 up to t is 2. Let's do that now. So plugging in t equals 2, we have negative 8 times 2 to the negative 1, which is 1/2. And then for the lower bound, we have negative 8 times 1 to the negative 1, which is still just 1. So we end up with negative 4 minus negative 8, which is 4. So the second integral evaluates to 4. Taking a look at the third, again, we want to start by taking the antiderivative of this function. Here we're missing a dx, so we'll add that in right now. So how do we take the antiderivative of cosine of x? Well, to do that, we want to ask ourselves, what function has cosine of x as its derivative? And our answer to that is sine of x. So the antiderivative of cosine of x is sine of x, and we can't forget the 2, the coefficient out front. Just like before, the antiderivative of 3 is going to be 3x. And we're evaluating this one from x equals 0 up to x equals pi. So when we plug in, we get 2 sine of pi plus 3 pi minus 2 sine of 0 and then plus 0. Well, sine of pi and sine of 0, if we remember from trig, those are both going to be 0. So this entire integral simplifies down to 3 pi. One question that many people have when we look at these integrals is why aren't we using plus c when we're taking the antiderivative? I know when we were just taking the antiderivatives last week before in discussion, we did have the plus c, but here we're just kind of ignoring it. Maybe we should be putting a plus c right here. And the reason is that when we evaluate, when we do this subtraction, well, we would have a plus c joining this first bracketed term, and we'd have a plus c in the second one. And since we're doing subtraction, those are just going to cancel it anyway. We're going to have c minus c. And so we just don't bother writing it when we're doing these integrals, these definite integrals, integrals with bounds. Now let's take a look at part D. Here, we see that we have a product of two functions. We have 7x times x cubed plus 2. And our first inclination might be to use something kind of like the product rule that we had for derivatives in the antiderivative. But unfortunately, we don't really have an easy product rule or quotient rule for antiderivatives. We have some other more complicated rules, but we don't need to worry about them in this course. Instead, we want to think about, is there a way that we can make this function, make this product look like something we know how to take the antiderivative of? And in this case, we can just distribute the 7x through the x cubed plus 2 to rewrite the integral as 7x to the 4th plus 14x. Right? And now each of the terms of this new function are just power, so we can use the power rule. So doing that, we get x to the 5th, and then divide by 5, and then x squared, and divide by 2. And we're evaluating this from -1 to 2. Okay, now we want to be careful with our signs this time when we're evaluating, because we have this -1 in our lower bound. So plugging in the 2, we get 7/5 times 2 to the 5th plus 7 times 2 squared. And then we're going to have minus 7/5 times -1 to the 5th plus 7 times -1 squared. Okay. Now I'm going to get a common denominator of 5 as I'm simplifying, because that's going to make the addition and the subtraction easier later. So I have 2 to the 5th times 7, which if you use a calculator gives us 224 over 5. And then our next term is going to be 28, which is 140 over 5. And the next one is -1 to the 5th, which is -1 times 7/5. So that gives me minus -7/5. And then we have plus 7, which is 35 over 5. And when we finish this, if we compute this out, we're going to end up with 336 over 5. So a common mistake that people make here is they forget to distribute this minus sign right here through all of the terms in the second evaluation. A lot of people will drop minus signs and make some sign errors here, so be very careful of that when you're doing these computations. Last, let's take a look at E. Like we said before, we don't have an easy quotient rule that we can use when we're taking the antiderivative. So instead, we want to, again, get this into a form that we know how to take the antiderivative. Hopefully get this into the form of just powers of x. And we can do this, again, by distributing the denominator across each of the terms in the numerator. Using our laws of exponents, we have t to the -2 plus 9t squared dt. And now we can use the power rule again to take the antiderivative. We're going to get t to the -1 with a minus in the front plus t cubed. 9 divided by 3 is 3. And we're evaluating this one from 1 to 2. Sorry, from t equals 1 to t equals 2. Okay, plugging in the bounds, we have -1/2 plus 3 times 2 cubed minus -1 plus 3. Okay, so 3 times 2 cubed is 8, gives us 24. And now we have 24 plus 1 minus 3. So 25 minus 3 is 22, minus 1/2. Give me 21.5, which is the same as 43 halves. Okay, so for each of these examples in question number 3, we started by maybe manipulating that function inside of the integral to make it look like something we know how to take the antiderivative of. Then we took the antiderivative, mostly using the power rule for antiderivatives, and also we had that cosine x where we just had to kind of think about which function has cosine as its derivative. Once we computed the antiderivative, we plugged in the lower and the upper bounds of each of the integrals, and then we subtracted to get our answer. Next, let's take a look at question number 4. Here we're told to find the area of the shaded region. And the thing we want to notice is that the bottom edge of this first piece of the shaded region is the x-axis, and the top edge of the second piece is the x-axis. And we know that integrals are telling us about areas between a function, in this case, this parabola f of x equals x squared minus 2x, and the x-axis. So here, we're going to want to write some integral expressions for this area, and then we can compute the integrals just like we did in question 3 to figure out the area. Now, we said before that integrals were a form of signed area, which means that the integral is going to be positive when the area sits above the x-axis, and it's going to be negative when the area sits below the x-axis. And here, since we want to compute the total area, we need to get rid of this sign. We want all of the area to be positive. So we're going to need to split up our problem into 2 integrals. For the first piece, if we take the integral of this f of x from -1 to 0, well, that's going to give us the positive area above the x-axis right here in this triangle. And then, well, the other piece, this kind of half dome-shaped piece sitting below the x-axis, the integral of that piece, so from 0 to 2 of x squared minus 2x, is going to be negative. But we said we want to be computing the total positive area, so we want to subtract this to get our area. This is going to be our formula for the area. So take a second here, make sure that this looks correct, make sure you understand how we got this formula for the area of the shaded region. So just as a reminder, this first term is talking about this. Let me highlight that better for you. Is talking about this triangular region. And the second term here is talking about this half dome region right here. Let's go ahead and calculate these integrals. So again, we're going to take the antiderivative of the function on the inside. That's going to be x cubed. And then divide by the 3 minus x squared, and 2 divided by 2 is 1. And we're evaluating this one from -1 to 0. And then on the second one, well, it's the same function we're integrating, but we have different bounds. This time we're going from 0 up to 2. And now we can start to do the plugging in and evaluating this. So we have 1/3 times 0 minus 0 gives us 0 for the first upper bound, minus And then we have 1/3 times -1 cubed minus -1 squared. Minus, now I'm going to open a big old set of parentheses. Our upper bound on the second one is 1/3 times 2 cubed minus 2 squared. And we have minus, and then again when we plug in 0, we're going to get 0. Okay, now let's take this one term at a time. So we're going to get negative 1/3 times -1 gives us really positive 1/3. We have -1 squared is positive 1. And then we have 2 minus signs out in front of us, which are going to cancel. So we get positive 1 again. And then we have minus, and then 2 cubed is 8, divided by 3 is 8/3. And we have minus a minus, which is a plus. And we have 2 squared. Hold on 1 second. We need to have another minus sign here. -2 squared gives us 4. Okay, and now we clean this up. So we have 1/3 plus 3/3 is 4/3. 4/3 minus 8/3 is -4/3. And then our 4 is 12/3. So our final answer is 8/3. The total amount of area in the yellow and the purple regions is 8/3. So we want to check and kind of make sure that this makes sense. So 8/3 is between 2 and 3. Well, the yellow area looks like a triangle, and it has a base of 1 and a height of 3. So its area, we could use the formula for area of a triangle. And then the second one, well, we could kind of here look at this as another 2 triangles, each with base 1 and height 1. So we have 2 times 1/2 times 1 times 1. We're going to get 3 halves plus, so here we go, 2 times 1/2 is 1, which is about 2.5. So between 2 and 3. So yeah, our 8/3 does seem like a reasonable estimate or a reasonable calculation of the area. Taking a look at number 5, it says that Wolfram alpha tells us that the antiderivative of this function x times x squared plus 3 to the 10th is this other function, 1/22 x squared plus 3 to the 11th plus c. And it asks us, how can we check whether this answer is correct? And this all goes back to the idea of what is an antiderivative. The antiderivative of this function tells us what is the function that has x squared plus 3 to the 10th as its derivative. That's what the antiderivative is. And if Wolfram alpha is telling us that this function is the antiderivative, then we can check and make sure it's right by taking the derivative of the orange function and seeing if we get the red function back. So we want to compute the derivative of this function. And to calculate this derivative, well, we want to use our derivative rules. So first, the derivative of the first piece, well, the 1/22 is going to come down. For the x squared plus 3 to the 11th, we need the chain rule. So we're going to have 11 x squared plus 3 to the 10th times the derivative of x squared plus 3, which is 2x. And then our derivative of c, since c is a constant, is just going to be 0. And now we can clean this up. So we can cancel out the 11 and the 2, give us a 22 in the numerator. That cancels with the 1 over 22. We can get rid of the plus 0. And we see that this simplifies down to just x times x squared plus 3 to the 10th, which matches what they gave us up here. So yes, Wolfram alpha was correct, and this is the antiderivative of x times x squared plus 3 to the 10th. And lastly, let's take a look at supplemental exercise A. Here we're given the value of 3 integrals, and we want to use this information to find 2 more integrals. And here again, we're going to use the fact that the integral tells us the area under the curve between the bounds. So this first integral is telling us the area between 0 and 1. The second integral is telling us the area between 0 and 2. And the last one's telling us the area between 2 and 3. So if I draw a little picture for this, here's my number line. 0, 1, 2, and 3. And the first one tells us that between 0 and 1, the area is 1.46. The second integral tells us that between 0 and 2, the area is 16.45. And the third one tells us that between 2 and 3, the area is 1428.09. And question A is asking us, well, what is the area between 1 and 2? And once we have our diagram, we could see, well, that's just taking the orange area and subtracting the red area. So that's 16.45 minus 1.46, which gives us 14.99. So 14.99 is the area between 1 and 2. For part B, now we want to know the area from 0 all the way to 3. Looking at our picture again, this is going to be the orange area plus the purple area. 45 plus 1428.09. If we do that addition, we're going to get 1444.54. That's the total area. If we want to write out a formula for this, this would be that the integral from a to b of f of x dx is equal to, well, it's the sum of the pieces of the intervals. So from a to c plus from c to b. We just applied this for both part A and part B. All right, so there we go. We did a review of the fundamental theorem of calculus, this connection between integrals, antiderivatives, and derivatives. And then we used the fundamental theorem to answer some questions at the beginning of the worksheet about antiderivatives and integrals. And then mainly, the main tool we use the fundamental theorem for is to compute these definite integrals, to compute the area under a curve. And that's what we did for questions 3 and 4. So take a look at this and let us know if you have any questions. We'll be happy to answer those in office hours.